Starts our chapter Alkenes from Organic Chemistry. First, introduction. There are a number of homologous series of open chain hydrocarbons in which the different members contain lesser number of hydrogen atoms than the alkanes, having the same number of carbon atoms. Since they contain less than the maximum possible number of hydrogen atoms, such hydrocarbons are termed as unsaturated hydrocarbons. The unsaturated hydrocarbons having the general formula CnH2n are called alkenes. They are characterized by the presence of a double bond between two carbon atoms in the molecule. It is known as ethylenic or olefinic bond. Unlike alkenes, alkenes are quite reactive chemically. They can rapidly undergo reactions in which a molecule of the attacking reagent is added to the alkene molecule to form a product containing more atoms than were present in either of the reactants. Or in instance, ethylene, the first member of alkene series, reacts with chlorine to form a product with the formula C2H4Cl2. Since this product is an oily liquid, ethylene was also termed as olefiant gas, that is, oil forming gas. Thus, this series beginning with ethylene began to be referred to as olefins by the earlier chemists. It is interesting to recall that cycloalkanes also have the general formula CnH2n. Thus, alkenes, which are open chain unsaturated hydrocarbons, are isomeric with cycloalkanes, which are cyclic saturated hydrocarbons. Next is structure of alkenes. Alkenes are marked by the presence of a carbon-carbon double bond in their molecules. The doubly bond carbon atoms are in a state of sp2 hybridization as illustrated below by considering the structure of ethylene, the simplest alkene. The two carbon atoms of ethylene which are linked by double bond make use of three equivalent sp2 hybridized orbitals and an unhybridized p orbital in the formation of this molecule. One of the carbon-carbon bonds of ethylene is formed by the overlap of an sp2 orbital of one carbon with an sp2 orbital of the second carbon. Each of the four carbon hydrogen bonds is formed by the overlap of one of the remaining hybridized orbitals of each carbon with the 1s orbital of a hydrogen. The bonds thus formed are sigma bonds as the overlapping of orbitals takes place along their axes. Moreover, since all the three sp2 orbitals of each carbon lie in the same plane, all the carbon and hydrogen atoms of the ethylene are also coplanar. Thus, ethylene is a flat molecule in which each carbon is situated at the center of a triangle, at the corners of which are located two hydrogen atoms, and the other carbon atom is clear from the skeleton of the molecule as shown in Fig 11. Each carbon atom is left with an unhybridized half-filled p orbital at right angle to the plane in which the carbon and hydrogen atoms are lying. These p orbitals of the two carbon overlap sideways to form another carbon-carbon bond. Since the overlapping takes place only to a small extent in its formation, this bond is a weak phi bond, as shown in Fig 1.2. The bond consists of two electron clouds, one lying above the plane of carbon and hydrogen atoms and the other below it. It is evident that the two bonds comprising the double bond between carbon atoms are not equally strong. The sigma bond between the carbon atoms has a strength of about 398 kJ mole, while the phi bond has a strength of nearly 284 kJ mole. The total strength of the carbon-carbon double bond of ethylene, 682 kJ per mole, is no doubt greater than that of carbon-carbon single bond in ethane, 368 kJ per mole. In Fig 1.2, The A part is sideways overlapping of p orbitals, and second B part is phi bond consisting of two electron clouds above and below the plane of atoms. Each of the HCH bond angles in ethylene is 117.5 degree, while each of the carbon carbon hydrogen bond angles is slightly more than 121 degree. The carbon carbon double bond distance of ethylene is 134 pm, which is lesser than the carbon carbon single bond distance. This is because the effective size of sp2 orbital of carbon, which is involved in the formation of carbon carbon double bond, is lesser than that of sp3 high orbital, which takes part in the formation of carbon carbon single bond. As a result, length of the bond formed by the mutual overlapping of sp2 orbitals is shorter than the length of the bond formed by the overlapping of sp3 orbitals. Moreover, the sideways overlapping of p orbitals to form the phi bond also brings the carbon atoms closer together. Again, due to the smaller size of sp2 orbital in comparison between sp3 orbital, the carbon hydrogen bond distance in ethylene 109 pm or 1.09 A is lesser than in ethane 110 pm or 1.10 A. Next is nomenclature. First is common system. In this system, alkenes are given the general name of olefins. These individual members are named by replacing the suffix "ane" of the corresponding alkane by "ylene". In case of isomeric compounds, the position of the double bond is generally indicated by using Greek letters alpha, beta, gamma, etc. according as the double bond is at one end of the chain or increasingly away from it. Sometimes prefixes such as iso are also used for branched chain isomers. The common name of some alkenes are given ahead. Second IUPAC system. According to the system, the class name of the compounds is alkenes and the individual members are named as follows. First, the longest chain containing the double bond is chosen as the parent alkene and the corresponding word root is noted. Second, the suffix "ene" is added to the word root to denote the presence of carbon-carbon double bond. Third, the carbon chain is so numbered that the carbon atom preceding the double bond gets the lowest possible number, and this number indicates the position of the double bond. Fourth, the number indicating the position of the double bond is placed just before the name of the parent alkene or just before the prefix "ene." For example, 1-butene or but-1-ene. In case of complex molecules, the number representing the double bond is always just before the prefix "ene" exemplified above. Fifth, the name and positions of the side chains, if any, are suitably indicated before the name of parent alkene in alphabetical order. For example, methyl 1-pentene, 2-ethyl 1-pentene, 4-ethyl 5-methyl 1-hexene. If the same side chain is repeated two or more times, the prefix di, tri, etc. is added to the name of the side chain, but the prefixes di, tri, etc. are not taken into consideration while deciding the alphabetical order. For example, 5-ethyl 2,4-dimethyl 3-heptene. Alkaline groups. The monovalent group obtained by removing a hydrogen from a doubly bonded carbon is known as alkaline group. To obtain the name of a particular group, the terminal of the name of parent alkene is replaced by YL. For example, ethyl, ethanyl or vinyl, 1-propenyl, 2-propenyl. In case of monovalent groups obtained by removing a hydrogen atom from a carbon, then the doubly bonded carbon, the groups are usually known as special names. For example, allyl or 3-propenyl. So, isomerism in alkenes. Alkenes exhibit structural as well as stereo isomerism as described below. First is structural isomerism. The first two members of alkenes do not show structural isomerism, but the alkenes from C4H8 onwards can exhibit chain isomerism as well as position isomerism. There are three structural isomerism possible for the molecular formula C4H8. First is 1-butene, 2-butene, 2-methylpropene. It is clear that first and second are position isomers of each other. First and third are chain isomers, while and third show position as well as chain isomers. Similarly, C5H10 can have five structural isomers: 1 pentene, 2 pentene, 2 methyl 1 butene, 3 methyl 1 butene, 2 methyl 2 butene. Alkenes also show ring chain isomerism with cycloalkanes, for example, propene, cyclopropane. Second is hindered rotation around carbon carbon double bond, geometrical isomerism. The carbon carbon double bond is in ethylene and other compounds consist of a sigma bond and a phi bond. The phi bond involves the overlapping of unhybridized phi orbitals of the two carbon atoms above and below the plane of the atoms. Because of this type of overlapping rotation around carbon carbon double bond is strongly inhered and can take place only if the phi bond breaks, but this would require about 284 kilojoule of energy per mole, which is not available to the molecules at room temperature. Due to hindered rotation around carbon carbon double bond, the relative position of groups attached to doubly bound carbon atoms get fixed. As a result, several higher alkenes and other substituted products can exhibit geometrical isomerism, that is, they can exist in two distinct isomeric forms which differ from each other in the relative distribution of groups in space around the double bond. For example, 2-butene can exist in the following two forms: cis and trans. Cis 2-butene, trans 2-butene. For details of geometrical isomers. Fifth is relative stabilities of alkenes. Even though all alkenes contain a carbon carbon double bond in their molecule, different alkenes have appreciably different stabilities. Their relative stabilities are generally determined on the basis of heats of hydrogenation. Heat of hydrogenation of an unsaturated compound is the quantity of heat evolved when 1 mole of the compound is completely hydrogenated. It has a value of nearly 125 kilojoule for almost every alkene through the although the actual values vary slightly from one member to another as shown in table 1.1. These values give quantitative information about the relative stabilities of alkenes. For instance, the heat of hydrogenation of trans 2-butene is 115.4 kilojoule, while that of cis 2-butene is 119.6 kilojoule. Each of these reactions uses up 1 mole of hydrogen and gives the same product, that is N-butene. Still, if trans-2-butene evolves about 4 kilojoule of energy less than cis isomer, this means that it contains about 4 kilojoule of energy less. Therefore, it must be more stable of the two isomers. Similarly, any other alkene which has lesser heat of hydrogenation than other isomer must be more stable. Thus, the heats of hydrogenation of different alkenes lead to the following conclusions. First, in case of dialkyl derivatives of ethylene, which exist as geometrical isomers, a trans alkene is slightly more stable than the cis isomer. This is because in the trans isomer, the two larger substituent groups are far apart from each other as compared to cis isomer. Therefore, there is lesser crowding and lesser van der Waals strains in trans isomer, and hence its greater stability. For examples, trans 2-butene, larger groups far apart; cis 2-butene, larger groups closer. Second, the more the number of alkyl groups attached to the doubly bound carbon atoms, the greater the stability. Therefore, the other of relative stabilities is this. The above order can be explained in terms of hyperconjugation. The greater the number of alkyl groups attached to doubly bound carbon atoms, more is the number of alpha hydrogens. Therefore, there is greater possibility of hyperconjugative interaction. This, in turn, would give rise to greater number of resonance structures, or in other words more extensive delocalization. Hence such alkenes would acquire greater stability. For example, two butene, two alkyl groups attached to doubly bound carbons, 6 alpha hydrogen, more hyperconjugative interaction, greater stability. Second is 1 butene, one alkyl group attached to doubly bound carbon, only two alpha hydrogens, lesser hyperconjugative interaction and lesser stability. The next is general method of preparation. The alkenes, particularly the lower members, are obtained commercially by the cracking of higher fractions of petroleum followed by fractional distillation. In addition, different laboratory methods are also available for their preparation in a pure form. Most of these methods involve elimination of appropriate groups from adjacent carbon atoms as discussed below. First, dehydrohalogenation of alkyl halides. This reaction involves the removal of elements hydrogen and halogen from adjacent carbon atoms of an alkyl halide by treating it with an alcoholic solution of potassium hydroxide. For example, ethyl chloride plus KOH alcoholic gives the product ethylene plus KCl plus H2O. Mechanism as dehydrohalogenation of alkyl halides takes place as follows. The base, such as hydroxide ion obtained from alcoholic potash, abstract a proton from a beta carbon, that is, the carbon which is next to the carbon carrying the halogen atoms. At the same time, the halogen is eliminated as a negative halide ion, and the electron pair of the carbon hydrogen bond left behind after the removal of H positive ion is used to form the second bond between carbon atoms. It has also been observed that dehydrohalogenation generally involves the removal of hydrogen and halogen substituted in transposition with respect to each other. The energy required for the cleavage of carbon, hydrogen, and carbon X bond comes from first, formation of bond between the base ions and the abstracted H positive ion. Second, formation of second bond between carbon and atom. And third, solvation of halides ions, which is accompanied by release of considerable energy. It should be noted that the reaction does not take place in a stepwise manner but involves a concerted mechanism. This mechanism, commonly known as E2 mechanism, E for elimination, 2 for biomolecular, involves a single step biomolecular elimination process. The reaction follows second order kinetics, and the rate of reaction depends upon the concentration of both hydroxyl ion and alkyl halides. Orientation of dehydrohalogenation and isoformation of alkenes. Regiochemistry. With several higher alkyl halides, the elimination of hydrogen from different carbon atoms is possible. This leads to the formation of a mixture of isomeric alkenes. In such cases, for example, 2 butene is more stable than 1 butene. The mixture formed in such cases contains the most stable alkene in predominating quantities. As already explained, the order of stability of alkenes is determined by the number of alkyl groups attached to the doubly bound carbon atoms. The more the number of alkyl groups, the greater the stability. As such, the relative order of stabilities is Cr2 double bond Cr2 is greater than Cr2 double bond Chr is also greater than Cr2 double bond Ch2 or RCH double bond CHR is greater than RCH double bond CH2 is also greater than CH2 double bond CH2. This also represents the order of A's of formation of alkenes in dehydrohallucination, since the more stable the alkene, the more easily it is formed. In the above observation can be justified in terms of the transition state leading to the formation of the alkene. It may be seen that in the transition state, the double bond between carbon atoms has begun to form, and therefore the transition state has acquired some of the alkene character. As such, the alkene and the transition state would have the same order of stability. Now, a more stable transition state would have lower energy and would be therefore formed more easily. As such, the more stable alkene would also be formed more easily. Next is Seitzeff's rule. Seitzeff's gave a generalization to predict the orientation of dehydrohalogenation on the basis of relative stabilities and ease of formation of possible alkenes. According to Seitzeff's rules, when an alkyl halide can undergo elimination in two different ways, forming a mixture of two products, the preferred product is the alkene, which is more highly alkylated at the doubly bound carbon atoms. For instance, in the dehydrohalogenation of sec-butyl chloride, 2-butene is the preferred product as it is more alkylated and therefore more stable and easier to form than 1-butane, which is the product, other product form. Reactivities of alkyl halides and hydrohalogenation, it has been found that for alkyl halides with a given alkyl group, the rate of elimination varies with the nature of X in the order Ri is greater than Rbr, greater than Rcl, greater than Rf. For a given halogen atom, the order of reactivity different alkyl halides is tertiary is greater than secondary is greater than primary. This is because branching at the carbon carrying the halogen increases in going from primary to secondary to tertiary alkyl halide. Now, the greater the branching, the number of beta hydrogen which can be attacked by the base, and therefore the higher the probability of attack. Moreover, the more branched alkyl halide leads to more branched and therefore more stable alkenes. Now the transition state for more stable alkene is also more stable and requires lesser act. This means that ease of elimination is maximum for tertiary alkyl halide. Next comes secondary, while the primary halides comes last. Next is dehydration of alcohols. On heating with sulfuric acid or phosphoric acid, or on passing their vapors over heated alumina or Lewis acid, alcohols get dehydrated to form alkenes. The exact reaction conditions vary with the nature of alcohol taken. For example, ethyl alcohol, the heat in the presence of H2SO4 96% and the temperature is 443 Kelvin and gives the product of ethylene plus H2O. Second example is tertiary butyl alcohol. Heat in the presence of 20% sulfuric acid and 355 Kelvin, which gives the product 2-methylpropene plus H2O. Mechanism: the dehydration of alcohols is the unimolecular elimination, which involves the formation of a carbocation as an intermediate. The reaction is believed to take place in three steps. In the first step, alcohol combines with the hydrogen ion to form a protonated alcohol. The second step involves the dissociation of protonated alcohol and formation of the carbocations. Finally, the carbocations loses a hydrogen ion to yield the alkene. The various steps are illustrated below with the help of ethyl alcohol. As we can see, ethyl alcohol plus acid. This reaction is fast and gives the protonated alcohol plus H2. All the three steps shown above involve reversible equilibria. However, the resulting alkene is much more volatile than the starting alcohol and is easily driven out from the reaction mixture. This shifts the equilibrium in step 3 towards the right. Consequently, the entire reaction is pushed to completion. It may be noted that the dissociation of protonated alcohol, step 2, requires the supply of energy. This is made available through the solvation of carbocation, considerable energy being released by the setting up of ion dipole bonds between the carbocations and solvent molecules. Evidence in support of the mechanism. The above mechanism is supported by the following observations. First, relative ease of dehydration of alcohols. It has been observed that the ease of dehydration of different cases of alcohols follows the order tertiary is greater than secondary is greater than primary. This observed order can be justified in terms of the rate determining steps in the process of dehydration, which involves the dissociation of protonated alcohol to form carbocation. It is apparent that the greater the stability and ease of the formation of the carbocation formed in the rate determining step, the greater the tendency of the alcohol to change into the carbocation. Now the order of stability and ease of formation of carbocation is tertiary is greater than secondary is greater than primary. Tertiary alcohol undergo dehydration most readily because they form the tertiary carbocation which is more stable. Once formed, the carbocation rapidly changes into the alkene. In the same way, secondary alcohols would be more easily dehydrated than primary alcohols, which would be relatively most difficult to dehydrate. Second, orientation to dehydration. Reduced selectivity. Many alcohols give rise to a mixture of isomeric alkenes on dehydration, but one of the alkenes is formed in predominantly large amounts. Such a reaction which can yield two or more structural isomers, but it actually produces only one isomer as the sole of product or the predominant product is said to be regioselective. For example, dehydration of secondary butyl alcohol over H3PO4 on alumina at 298 Kelvin yields the mixture of 75.9% of 2-butene and 24.1% of 1-butene. But the isomeric butenes are obtained by the expulsion of a H positive ion from the same carbocation formed as an intermediate as shown below. Therefore, the stability of carbocations cannot have any effect on the higher than expected amount of 2-butene formed. It may be noted that, however, that the 2-butene is more stable than 1-butene since the former is more highly substituted. This means the reduced selectivity in the dehydration of alcohols is due to greater stability of the main product. A similar situation exists in the dehydration of 2-methyl 2-butanol with 15% of H2SO4 at reflux temperature. Here again, the more highly substituted product and therefore more stable product is formed in predominating quantities. To sum up, it may be selected that reduced selectivity in dehydration of an alcohol is consistent with the formation of more stable alkene. Third, rearrangement of carbocations and formation of unexpected products during dehydration. It has been found that during the dehydration of alcohol, some of the alkenes formed are not what one would normally expect. The position of double bond formed or sometimes even skeleton may be quite unexpected. For example, the dehydration of an butyl alcohol gives a mixture of two butene main product and one butene, whereas normally only one butene should be formed. The formation of unexpected products as shown above can be explained in terms of the rearrangement of intermediate carbocations. It have been observed that the carbocations tends to rearrange to form more stable ions. And this rearrangement usually involves the migration of a hydride ion from an adjacent carbon atom to the positively charged carbon of the carbocation. Such a migration is known as hydride shift. Alternatively, the rearrangement may occur through the migration of an alkyl group with its pair of bonding electrons from an adjacent carbon to the carbon having the positive charge. This type of migration is known as alkyl shift. Since such migrations generally involve only adjacent carbons, they are also termed as one-to shift. Example of hydride shift and the hydration of n-butyl alcohol. The intermediate carbocation initially formed is n-butyl carbocation, which is a primary ion. This undergoes a 1,2 hydride shift to form the more stable secondary butyl ion. This ion in turn loses a H positive ion to form the more stable 2-butene as the preferred product. Example of alkyl shift and the dehydration of 3,3-dimethyl-2-butanol. The carbocation initially formed is the secondary carbocation, that is 3,3-dimethyl-2-butyl ion. This undergoes the migration of a methyl group with the bonding pair of electrons from an adjacent to the positive carbon to form the more stable tertiary carbocations, namely 2,3-dimethyl-2-butyl ion. The ion thus formed loses a hydrogen ion to form 2,3-dimethyl-2-butene as the main product, which is more stable than expected product 3,3-dimethyl-1-butene. Third is dehalogenation of vicinal dihalides. When heated with zinc in alcoholic solution, a vicinal dihalide gets dehalogenated to form an alkene. The major limitation of the reaction is that weak dihalides are themselves usually obtained by the addition of halogenation to make alkene. As such, this is not a very practical method for the preparation of alkenes. Mechanism: dehalogenation is a biomolecular elimination reaction, that is E2, which proceeds as follows. Weak dihalides transition state, then C double bond C plus ZnX2. Fourth is controlled reduction of alkynes. The controlled reduction of an alkyne to the alkene stage may be brought about with hydrogen in the presence of a special catalyst, palladium, palladium supported on CaCO3, partially poisoned by lead acetate and known as Lindelar, Lindelar's catalyst, or a nickel boride catalyst known as P2, or with sodium or lithium in liquid ammonia. Where the alkene can exist in situ trans from the catalyst reduction yields mainly cis alkene, while the other method produces predominantly trans alkene. The mechanism of trans addition with alkali metal ammonia is discussed in chapter 7. Fifth is pyrolysis of quaternary ammonium hydrides. Hofmann elimination. When tetraalkyl ammonium hydroxide is heated strongly 400 Kelvin or higher, it undergoes elimination reaction known as Hofmann elimination to form an alkene. For example, trimethyl and propyl ammonium hydroxide heat and gives the product prop- propylene plus trimethylamine plus H2O. The quaternary ammonium hydroxide used in the reaction is obtained by reacting an amine with the excess of methyl iodide. The process is known as exhaustive methylation, followed by reaction with the silver oxide. For example, trimethyl and propyl ammonium hydroxide used in the above reaction is obtained as follows. Mechanism The mechanism of a Hofmann elimination involves the removal of a proton from a beta carbon of the quaternary ammonium ion. At the same time, there is rearrangement of electrons. Carbon nitrogen bond breaks and the carbon carbon bond is formed. The mechanism is quite similar to that of dehydrohalogenation of alkyl halides. However, in contrast of contrast to dehydrohalogenation of alkyl halides, more where more highly substituted alkenes is the major product. The alkene preferably formed in Hofmann elimination is the one that is least substituted. For example, 1-methyl-butyl trimethyl ammonium hydroxide is heated and gives the 1 pentene, which is 96%, plus 2 pentene, which is 4%. The reason for this selectivity is not clearly understood, but it appears that OH abstract a proton from the last hindred position in the alkyl group. Next is physical properties. First is physical state. The first three members of alkenes are gases, the next 14 are liquids, while the higher members are solid, with the expectations of ethylene, which has a faint sweet odor. All other members are odorless and colorless. Physical Second is physical constants. The boiling point of alkenes increase regularly with the increasing number of carbon atoms. Almost isomeric alkenes branched chain members have lower boiling points. The melting point and specific gravities of alkenes also show a regular gradation, but it as in case of alkanes, the maximum specific gravity of alkenes is about zero point 0.8. This means that the alkenes are lighter than water. Third is solubility. The alkenes are practically insoluble in water but freely soluble in organic solvents such as benzene, ether, and carbon tetrachloride. Fourth is polarity. The trans isomers of symmetrical alkenes are nonpolar in character, but the unsymmetrical alkenes and the cis isomers of symmetrical alkenes are somewhat polar and have small dipole moments. Being somewhat polar, cis alkenes have slightly higher boiling points than their cis trans isomers. On the other hand, being unsymmetrical, cis tra- isomers are not so closely packed in the solid state and therefore they have lower melting points than the trans isomers. Next is chemical properties of alkenes. The carbon carbon double bond, which is a characteristic feature of every alkene, consists of strong bond sigma bond and a weak bond phi bond. As can be reasonably expected, the phi bond breaks up rather easily when attacked by chemical reagents, and two strong sigma bonds are formed in its as shown below. Thus, the typical reaction of alkenes are addition reaction, which involves the union of two reacting molecules to yield a small molecule of the product. A majority of the addition reaction of alkenes are initiated by electrophilic reagents, since the electron pair of the phi bond in alkenes serves as a source of electrons. But apart from electrophilic addition reaction, alkenes are also undergo some free radical addition reaction and even some substitution and cleavage reactions. The important reactions are discussed below. First is addition reaction, and the first part is addition of hydrogen. In the presence of certain finely divided metals such as platinum, palladium, or nickel, hydrogen adds on to alkenes to form alkane. The temperature and pressure employed in the reaction vary with the nature of the catalyst. Alkene plus H2 undergoes in the reaction with the nickel, palladium, or platinum and gives the alkane. For example, ethylene plus H2 A reaction with platinum at temperature 300 Kelvin gives the ethane. The reaction proceeds quite rapidly in the presence of suitable catalyst, but it is very slow in its absence. The finely divided metallic catalyst helps the reaction by absorbing the reactant molecules on its enormous surface and breaking the pi bond of the alkene. As already discussed, hydrogenation of alkenes is very useful in determining the relative stabilities of alkenes. Mechanism of hydrogenation. Hydrogenation of alkenes is the heterogeneous reaction which takes place on the surface of solid catalyst particles in a stepwise manner. To start with, the catalyst adsorbs hydrogen on its surface. This is followed by the formation of a complex between the catalyst and the alkene. A stepwise transfer of hydrogen atoms to the alkene then takes place. The alkene thus produced finally diffuses out of the catalyst surface. It is interesting to note that both hydrogen atoms add to alkene from the same side of the molecule. This is known as sign addition. Electrophilic addition reaction, the most important addition reaction of alkenes which involve electrophilic addition mechanisms are as follows. Second, addition of hydrogen halides. Alkenes readily undergo addition reaction with hydrogen halides HCl, HBr or HI to form alkyl halides. For example, ethylene plus HI gives the ethyl iodide. Mechanism. The addition of hydrogen halides to alkenes takes place by a two-step electrophilic mechanism. Step 1, which controls the overall rate of reaction, involves the transfer of proton, that is hydrogen without its electrons, to the alkene to form a carbocation. In doing so, one of the doubly bound carbon atom uses the pi electron informally shared with the other carbon, which is rendered electron deficient. This is followed by step 2, in which the carbocation and the negative halide ion combine to form the final product. Alkene plus HX slow reaction gives the carbocation plus halogen. And similar to next reaction, third is addition to unsymmetrical alkenes. Markovnikov rule. In case of unsymmetrical alkenes, the addition of hydrogen halides, any other similar reagent which consists of two different atoms or groups, can give rise to two isomeric products. For example, when hydrogen iodide adds to propylene, formation of two product is possible as below. Propylene plus HI gives the N-propyl iodide and isopropyl iodide. It is, it is observed, however, that actually isopropyl iodide is the main product and N-propyl iodide is formed in very small quantities. A careful study of many addition reactions of this type enabled Markovnikovs to initiate enunciate a rule known as Markovnikov's rule. The rule states that when addition across an unsymmetrical ethylenic bond takes place, the positive part of the attacking reagent goes to the carbon with the greater number of hydrogen atoms. Theoretical justification of the rule. Markovnikov's rule can be easily justified in the terms the the iconic mechanism of the addition reaction. For instance, let us consider the addition of hydrogen iodide to propylene, which yields isopropyl iodide as the predominating product as stated above. The reaction can be initiated by the addition of electrophilic particle proton to one of the doubly bounded carbon atoms to form either carbocation 1 or 2. Carbocation 1 is a secondary carbocation while carbocation 2 is a primary carbocation. On the basis of ease of formation and relative stabilities of carbocations, carbocation 1 would naturally be formed faster than n in preference to carbocation 2. Reaction to this preferred carbocation with the iodide ion would yield isopropyl iodide as the main product. Similarly, the addition of HCl to isobutane butylene, butylene. The product obtained is almost only tertiary butyl chloride. This is because the intermediate carbocation is the formation of tertiary chloride is a tertiary ion 3, which is naturally formed in presence to the other possible carbocation 4, a primary ion. As such, the final product is obtained by reaction between chloride ion and the tertiary carbocation. Modern version of Markovnikov's rule. On the basis of our present knowledge of mechanism of addition reaction of alkenes, Markovnikov's rule may also be stated as addition to ethylenic double bond involves the intermediate formation of more stable carbocation. Anti-Markovnikov's rule addition peroxide effect. It has been observed that in the presence of peroxides, the addition of hydrogen bromide to alkenes takes place against the Markovnikov's rule. For example, when propylene is treated with hydrogen bromide in the presence of traces of benzoyl peroxide, the predominant product obtained in N-propyl bromide and not isopropyl bromide expected according to Markovnikov's rule. But in the addition of hydrogen bromide is carried out in the presence of peroxides, the reaction takes place in accordance with Markovnikov's rules. The action of peroxides to cause the anti-Markovnikov's addition of hydrogen bromide is known as peroxide effect. It was discovered by Karash. It should be carefully noted that peroxides have no effect in case of the addition of other reagents such as hydrogen chloride, hydrogen iodide, sulfuric acid, water, etc. Free radical mechanism of anti-Markovnikov's addition. To account for the peroxide effect, it has been proposed that anti-Markovnikov's addition in the presence of peroxide takes place through free radicals and not through ionic particles as explained below. The initial step in the free radical mechanism is the decomposition of peroxide to yield free radicals. The free radical thus formed abstracts hydrogen from hydrogen bromide to form bromine free radical. Step 2. Bromine radical turns add on the double bond and thus converts the alkene into another free radical. Step 3. This free radical abstracts a hydrogen from another molecule of hydrogen bromide to form the final product as well as a bromine radical. Step 4. This bromine radical continues the chain by repeating the step 3 and 4 as depicted below. The step 1 and 2 are initiation steps, while the step 3 and 4 are which are repeated again and again constitute chain propagation steps. This mechanism is supported by the fact that only a small quantity of peroxide is needed for the process because it is required only for initiating the reaction. Similarly, the fact that addition a small quantity of a inhibitor such as hydroquinone can prevent the addition according to peroxide effect also supports the mechanism. The inhibitor can obviously break the chain process by forming unreactive particles. Let us now consider the addition of HBr to an unsymmetrical alkene in the presence of peroxide according to the above mechanism. As we see this mechanism, in step 3, bromine free radical preferentially adds to C1 of propylene to produce a secondary free radical. If the bromine were to add C2, the radical formed would be primary free radical, which is less stable than the secondary radical. The reaction of secondary radical with HBr in step 4 naturally gives rise to N-propyl bromide. Thus, the anti-Markovnikov addition of HBr can be justified in the terms of the ease of formation and stabilities of intermediate free radicals formed in chain propagating. Step 3. Relative reactivities of alkenes in electrophilic addition reaction. Con- the rate controlling step in the electrophilic addition of halogen acids to alkenes in step 1, which involves the formation of carbocations. It has also been learnt that The ease of formation and relative stabilities of carbocations follows the order tertiary is greater than secondary is greater than primary. This means that an alkene which gives rise to a tertiary carbocation would undergo addition more readily than another which forms a secondary carbocation. Similarly, the alkene forming a secondary carbocation would be more reactive than one which forms a primary carbocation. In short, the relative reactivities of alkenes depends upon the ease of formation and stabilities of intermediate carbocations. As such, the alkenes show the following order of reactivities towards electrophilic addition reaction. R2C double bond Cr2 is greater than Cr2 double bond Chr is greater than Cr2 double bond Ch2, or RCH is double bond CHR is greater than RCH double bond CH2 is greater than CH2 double bond CH2. Of substituted alkenes, the relative reactivities are determined by the nature of the substituent groups. If the substituent group is an electron attracting group such as halogen, it destabilizes the intermediate carbocation and decreases its ease of formation. In other words, such group decreases the reactivities. For instance, the reactivity of CH2 double bond CHBr is less than that of CH2 double bond CH2 because of the presence of electron attracting bromine. On the other hand, presence of electron releasing group stabilizes the developing carbocation and increases its ease of formation. So, as such, these groups contribute towards greater activity. Third, addition of sulfuric acid. Cold concentrated sulfuric acid adds on two alkenes to form alkyl hydrogen sulfate. Alkene plus sulfuric acid gives the alkyl hydrogen sulfate. For example, ethylene plus H2O gives the ethyl hydrogen sulfate. Mechanism. The mechanism of addition is similar to that in case of hydrogen halides and may be depicted as shown below. As we can see, it, ethylene plus H2SO4 is a slow process, then carbocation plus hydrogen sulfate ion will be product. The next reaction is fast and we get the alkyl hydrogen sulfate. It may be pointed out that alkyl hydrogen sulfates are easily hydrolyzed to form alcohols. For example, ethyl hydrogen sulfate plus H2O heated and gives the ethyl alcohol plus H2SO4. As such, addition of sulfuric acid to an alkene followed by hydrolysis with water constitutes a convenient method for the manufacture of alcohol such as ethyl alcohol, isopropyl alcohol, etc. Fourth is addition of water. The more reactive alkenes directly add in water in the presence of dilute acids to yield alcohols. Alkene plus H2O in the presence of hydrolysis gives the alcohol. Next is mechanism. This reaction also takes place by electrophilic addition mechanism similar to the addition of protic acids as shown below. As we can see. Fifth is addition of halogens. Alkenes undergo addition of chlorine and bromine at room temperature in an inert solvent like carbon tetrachloride to form vicinal dihalides. Alkene plus X2, which can be chlorine or bromide, gives the weak dihalide in the presence of CCl4. For example, propylene plus Br2 in the presence of CCl4 gives the propylene pylene dibromide. In the reaction of alkene with bromine, the red color of bromine is discharged due to the formation of dibromide which is colorless. Therefore, the reaction is used as a test for the presence of carbon double bond in a molecule. Addition of fluorine to alkenes is not came out since it causes extensive cleavage of the molecule. In case of addition of iodine, Vicinal diiodides formed are highly unstable and eliminate iodine immediately to reform the double bond. It may be noted that unlike halogen substitution of alkanes, the addition of halogens to alkenes gives only one product in nearly quantitative yield. Mechanism. It was believed earlier that addition of halogen to alkenes takes place through electrophilic addition process involving carbocation intermediates as in the reactions with halogen acids and other protic acids discussed so far as below given. Halogen molecule is normally nonpolar in nature, but as it comes close to the alkene molecule, the pi electron cloud of the double bond begins to repel the electron cloud of halogen molecule. As a result, the electrons of halogen molecule gets displaced towards the halogen atom away from the alkene molecule. This results in polarization of the halogen molecule. The atom nearer to alkene becoming relatively positive and the other negative. The positive halogen of the polarized molecule is immediately abstracted by the alkene to form an intermediate carbocation and a negative halide ion. This constitutes the rate controlling step of the reaction. In the second step, the carbocation and negative halide ion combine to yield the dibromide, non-polar halogen molecule approaching the alkyl molecule in the presence of pi electron cloud and gives the polarized halogen molecule. Next is the two-step ionic mechanism is supported by the fact that in the presence of anions of another halogen, the addition reaction with a given halogen gives a product containing different halogen atoms in addition to the normal product. For example, in the presence of Cl negative ion, addition of bromine to ethylene gives a mixture of CH2b or bond CH to Cl. This is because carbocation formed in the first steps can react either with bromide ion or chloride ion to form two different products. Limitations of above mechanism. The mechanism described above fails to explain two important observations. Stereochemistry of addition of halogens. The addition of halogen to an alkene proceeds almost completely in trans manner. According to the above mechanism, the addition of second halogen to the carbocation formed in the first step could take place either from the same side or from the opposite side. Second is non-formation of rearranged products. Reaction involving carbocation intermediates as postulated in above mechanism should be accompanied by the formation of rearranged products wherever possible, but there is no formation of rearranged products during the addition of halogen to alkenes. Next is cyclic halonium ion mechanism. To overcome the limitation of the above mechanism, it has been suggested that the addition of halogens to alkenes involves the formation of a new kind of cyclic ion known as halonium ion rather than a simple carbocation as explained below. As the halogen molecule approaches the alkene and gets polarized, the positively polarized halogen and forms a phi electron with the phi complex with the phi electron of the alkene. The complex in turn undergoes heterolytic cleavage of halogen-halogen bond, giving rise to a cyclic halonium and a negative halide ion. The halonium ion has a halogen atom bonded to two carbon atoms by a sigma bond to each. Finally, the halide ion produced above attacks one of the carbon atoms of the halonium ion, giving rise to the formation of the halides by transaddition. Mechanism of involving electrophilic addition to alkenes through the intermediate formation of cyclic halonium ion was initially proposed to explain the observation that the reaction leads to transaddition. This stereospecific nature of the reaction cannot be justified if the addition were to take place through the intermediate formation of carbocations, as in the addition of protic acids. In the last few years, there has been some evidence to prove that the cyclic halonium ions do actually exist. Sixth, formation of halohydrines. The reaction between alkenes and chlorine or bromine in the presence of water leads to the formation of halohydrines, that is, compounds containing halogen and hydroxyl groups on adjacent carbon atoms is in addition to dihalo derivatives. Alkenes plus X2, which can be chlorine and bromine, plus H2O gives the halohydrine plus HX. For example, ethylene plus Br2 plus H2O gives the ethylene bromohydrine plus HBr. Mechanism: the overall reaction consists in the addition of elements of hypohalous acid HOX, but the actual process proceeds through the attack by polarized followed by water as shown ahead. As we can see, next seventh, addition of alkanes, alkylation. Alkanes can also add on alkanes in the presence of utable acidic catalyst to form higher alkanes. The reaction known as alkylation is employed numerically for the manufactures of alkanes such as 2,2,4-trimethylpentane used as aviation fuel. Alkene plus alkane in the presence of hydrolysis gives the higher alkane. For example, isobutylene plus isobutane in the presence of H2SO4 gives the 2,2-trimethylpentane. Mechanism: alkylation is believed to take place through electrophilic mechanism involving the intermediate formation of carbocations. As shown below, isobutyl plus formic acid gives the tertiary butyl cation. Next is isobutane gives the 2 to 4 trimethylpentane. Eighth is addition of alkenes. Polymerization. Under suitable conditions, molecules of an alkene can add together to form large molecules called polymers. The reaction taking place is known as polymerization. Polymerization of alkenes is also known as addition polymerization or vinyl polymerization. A few examples of polymerization of alkenes are given below. First is formation of polyethylene or polythene. These days, two types of polythenes are produced which have widely different properties are given below. First is low density polythene. It is manufactured by heating very pure ethylene to 463 to 483 Kelvin under a pressure of about 1500 atmospheres in the presence of traces of oxygen 0.03 to 0.1%. Low density polythenes is chemically inert, tough but flexible and a very poor electrical conductor. Second is high density polythene. It is generally manufactured by heating ethylene in a hydrocarbon solvent to 333 to 343 Kelvin under a pressure of 6 to 7 atmospheres in the presence of catalysts such as triethyl aluminum and titanium tetrachloride, also known as Ziegler catalyst. High density polythene is also chemically inert but is tougher and harder and has greater tensile strength than low density polythene. Second is formation of polypropylene or polypropene. It is prepared by polypropylene through an hexane, which is an inert solvent and containing triethyl aluminum at 373 Kelvin under 10 atmospheric pressure. Polypropylene can also be manufactured by other methods and it possesses different characteristics depending upon its method of formation. Formation of or styrene. It is prepared by polymerization of styrene in the presence of benzoyl peroxide. Polystyrene is a lightweight material having good electrical properties. Next is hydroboration oxidation of alkenes. When treated with diborane BH3 whole 2, alkenes undergo hydroboration to form alkyl boranes. The alkyl boranes are readily oxidized by hydrogen peroxides in alkaline solution to form alcohols. Thus, the net result of this reaction also is the addition of water to alkenes to form alcohols. For example, ethylene plus BH3 whole 2 gives the ethyl borane, and after the addition of CH2 double bond CH2, it gives the diethylborane, and then also again the addition of CH2 double bond CH2, it gives triethylborane. In the first stage of hydroboration, addition of BH3 to the carbon-carbon double bond takes place with hydrogen getting attached to one carbon and borane to the other to form monoalkyl borane BH2R. In the second stage, BH2R adds to a second molecule of alkene to form dialkyl borane BHR2, which in turn adds to third molecule of alkene to form trialkyl borane Br3. The alkyl boranes are not isolated but are oxidized in the same reaction vessel when the boron part gets replaced by OH group to generate the alcohol. Orientation of hydroboration. The hydroboration oxidation is also a regioselective reaction, and the alcohol obtained is such as if anti-Markovnikov of addition of water to alkenes had taken place. As such, this method can be used for the preparation of alcohols which cannot be prepared by other methods of hydration of alkenes. For example, acid catalysts hydration as well as oxymercuration demercuration of propane yields to propanol, while its hydroboration oxidation gives rise to 1-propanol. Some more examples of hydroboration oxidation are as follows: 3,3-dimethyl 1-butene in the presence of B2H6 and H2O2 and OH negative ion gives the 3,3-dimethyl 1-butanol. Second is 2-methyl 2-butene in the presence of B2H6 and H2O2 and OH negative ion gives the 3-methyl 2-butanol. It may be noted that due to anti-Markovnikov orientation, only primary and secondary alcohols can be obtained by this method. Mechanism of hydroboration oxidation. Even through Even though the overall sequence of hydroboration oxidation of alkenes appears to go against the Markovnikov's rules, yet fundamentally this reaction also involves electrophilic addition to carbon-carbon double bond or as given below. First, hydroboration. As already stated, diborane behaves in its reaction as if were getting dissociated to form BH3. Now in BH3, boron has got only 6 electrons in its outermost energy level and is therefore highly electron deficient or acidic in nature. This electrophilic boron or borane seeks out to 5 electron of carbon-carbon double bond and begins to attach itself to the less substituted carbon of the double bond. As the electrons shift away from the more substituted carbons of the double bond, the carbon becomes more and more electron deficient. As such, it begins to take away a hydrogen attached to boron along with the pair of electrons of this hydrogen bond boron bond. In this way, we get a transition state which may be depicted as shown on the right. In the transition state, C2 still has a partial positive charge while B has a partial negative charge as the loss of 5 electron by C2 to C1. B bond is more than its gain of electrons by the partial formation of its bond with hydrogen. The transition state ultimately generates the alkyl boron in which BH bond has been cleaved and the new C2H bond has been completely formed. That is this. It may be noted that unlike ordinary electrophilic addition reaction, hydroboration does not involve the intermediate formation of carbocations. Next is oxidation of alkyl borines. The mechanism of oxidation of alkyl borines by alkaline hydrogen peroxide involves nucleophilic attack by hydroperoxide ion and may be summed up as follows. 10th is oxymercuration demercuration of alkenes. When treated with mercuric acetate in a water tetrahydrofuran solution, alkenes form hydroxymercurial compounds. These mercury compounds are reduced by sodium borohydride NaBH4 to yield alcohols, that is alkene plus mercuric acetate, and the presence of oxymercuration gives the alcohol. In the first step, water and mercuric acetate add to the double bond. This is known as oxymercuration. In the second step, sodium borohydride reduces the mercurial compound and the mercury acetate group gets replaced by the hydrogen. This is known as demercuration. Demercuration of alkenes. When treated with mercuric acetate in a water tetrahydrofuran solution, alkenes form hydroxymercurial compounds. These mercury compounds are reduced by sodium borohydride NaBH4 to yield alcohols. In the first step, water and mercuric acetate add to the double bond. This is known as oxymercuration. In the second step, sodium borohydride reduces the mercurial compound and the mercury acetate groups get replaced by the hydrogen. This is known as demercuration. Both the steps take place very rapidly and conveniently at room temperature. The organomercurial compound formed in the first step is not isolated, but it reduced in C2 by sodium borohydride to form alcohol in high yield le- less than 90%, greater than 90%. Oxymercuration demercuration is highly reagioselective and the alcohol formed is in accordance with Markovnikov's rule. Specific examples of the reaction are as follows. Like direct hydration of alkenes, alcohols formed in the reaction also correspond to Markovnikov's rules. Therefore, primary alcohols except CH3, CH2OH cannot be prepared by this method. The proposed mechanism for the reaction may be described as follows. Oxymercuration to start with electrophilic attack by the mercury species HGOAC. All the at the less substituted carbon of the double bond, that is the carbon which carries greater number of hydrogens, takes place to form a mercury bridged carbocation. This cation is immediately attacked by a nucleophilic solvent, that is water, to yield the hydroxy mercurial compounds as shown below. Second is demercuration. The hydroxymercurial compound undergoes the demercuration or reduction with NaBH4 to form alcohol. This mechanism is supported by the following facts. First is it can justify why orientation of addition corresponds to Markovnikov's rule, since Hg gets attached to carbon carrying greater number of hydrogens while OH goes to the carbon having less number of hydrogens. Second, it also explains the absence of rearrangement taking place during the reaction since no open carbocation intermediate is involved in the proposed mechanism which can undergo rearrangements. 11th is addition of carbenes. Alkenes undergo addition reaction with carbenes, both the singlet and triplet form to form cyclopropane derivatives. The reaction is also known as cycloaddition because the ring is generated as a result to the reaction. Since free carbenes are too reactive to be isolated, the reaction is usually carried out by using a carbenes precursor which generates the carbene under suitable experimental conditions. For example, when treated with diazomethane CH2N2 or ketene CH2 double bond C double bond O in the presence of light alkenes add on methylene to form cyclopropane derivatives. Mechanism of addition of singlet methylene. Addition of singlet methylene involves single step electrophilic addition. Being electron deficient in nature, singlet methylene seeks electrons from carbon carbon double bond. As a result, singlet methylene gets simultaneously attached to both the doubly bound carbon atoms. Therefore, stereochemistry of the reactant gets preserved in the product. Cis alkenes yield cis dialkyl cyclopropanes while trans alkenes yields trans dialkyl cyclopropanes. The complete mechanism may be depicted as this. Stereochemistry of addition of triplet methylene. Addition of triplet methylene is not non-stereospecific and leads to a mixture of products. For example, addition of triplet methylene to either cis-2-butene or trans-2-butene yields a mixture of cis and trans 1,2-dimethyl cyclopropanes. Next is mechanism of addition of triplet methylene. Triplet methylene reacts with alkenes in a two-step free radical mechanism. Triplet methylene is a diradical and it attacks the alkene to form an intermediate diradical having the conformation A. This diradical has a lifetime long enough for rotation of groups to take place around central carbon-carbon bond. This gives rise to conformation B. Ring closures of A and B leads to the conformation of both cis and trans products as shown below. Next is addition of substituted carbenes. Alkenes can also add on substituted carbenes such as dichlorocarbene to form cyclopropane system. For example, when 2-butene is treated with chloroform in the presence of potassium, tertiary butoxide 3,3-dichloro 1,2-dimethyl cyclopropane is formed. The reaction involves the addition of dichlorocarbene in the singlet form. It is stereospecific and takes place by electrophilic mechanism. The complete process may be shown as below. Next is addition of free radicals. It has been already discussed that the antimarconic of addition of hydrogen bromide to alkenes in the presence of peroxide takes place through a free radical mechanism. Since the discovery of peroxide effect in 1933, the addition of some other reagents to alkenes in the presence of peroxide or light has also been found to involve a similar free radical mechanism. For example, let us consider the addition of carbon tetrachloride to an alkene in the presence of a peroxide. Next is oxidation reaction. Alkenes form a variety of products on direct oxidation with different reagents under different conditions. While some of the oxidation reactions merely involve addition to the ethylenic bond, other brings water complete cleavage of the double bond. We will first discuss only the former type of reactions, while the latter type of reactions are discussed under cleavage reactions. Oxidation with aqueous potassium permanganate solution. When alkenes are treated with dilute aqueous solution of potassium permanganate, a hydroxy group is added to each of the doubly bound carbon atoms, resulting in the formation of vicinal glycols. The reaction takes place in a cis manner. and is commonly termed as cis hydroxylation. Alkene plus H2O plus O in the presence of KMNO4 gives the glycol. For example, propylene plus H2O plus O in the presence of KMNO4 give propylene glycol. As potassium permanganate gets decolorized in this reaction, it can be used as a test for the presence of ethylenic bond in a molecule. The test is generally called Bayer's test. Mechanism: the reaction is believed to take place through the formation of intermediate cyclic manganate species which get hydrolyzed to give the glycol. Besides aqueous potassium permanganate solution, osmium oxide OSO4 can also be used for bringing about hydroxylation. This reaction also involves cis hydrolation and proceeds through cyclic oximate intermediate. The intermediate is hydrolyzed with NaHSO3 solution to get glycol. Next is oxidation with peroxyacids. Epoxidation. Alkenes react with peroxy acids such as peroxyacetic acid or peroxybenzoic acid to form epoxides. Epoxides are compounds having three membered rings, one of the atoms of which is oxygen. The reaction involved in the formation of epoxides is sometimes referred to as epoxidation. Mechanism: this reaction involves the transfer of an oxygen atom of the peroxy acid to alkene. The reaction is believed to proceed by the following mechanism. Ethylene can also form an epoxy merely by heating in air in the presence of silver catalysts. Ethylene plus O2 in the presence of silver at 525 Kelvin temperature gives the ethylene oxide. Epoxides also form vinyl glycols on hydrolysis with boiling water, but it gives rise to trans product. Next is substitution reaction and this allylic halogenation. With the expectations of ethylene, all other alkenes contain one or more alkyl groups attached to one or both the doubly bound carbon atoms under suitable conditions. These alkyl groups can undergo substituent reactions similar to those of alkenes. For example, when propylene is treated with chlorine at 775 Kelvin, it undergoes substitution at the alkyl group rather than addition at the double bond. Propylene plus Cl2 at the temperature 775 Kelvin gives the alkyl chloride plus HCl. This type of reaction where substitution takes place at the alpha carbon atom with respect to the double bond is referred to as allylic substitution. The hydrogens attached to alpha carbon with respect to double bond are called allylic hydrogens. Mechanism: allylic substitution is believed to take place through free radicals mechanisms as in case of alkenes. An excellent reagent for the bromination of alkenes at the allylic position is an bromosuccinimide NBS. 16th is substitution at a vinylic position. An interesting reaction of alkenes is that they can undergo electrophilic substitution at the doubly bound carbon atom. For example, when an alkene is treated with an acid chloride in the presence of anhydrous aluminum chloride, it gives rise to an alpha beta unsaturated ketone. The reaction is comparable to Friedel-Crafts alkylation of benzene mechanism. In the presence of anhydrous AlCl3, acid chloride generates acylium iron which attacks the double bond to form a carbocation. The carbocation loses a proton to yield the alpha beta unsaturated ketone. Next is cleavage reactions, ozonolysis. Also undergo certain reactions in which the double bond is completely broken and the alkene molecules changes into smaller fragments. Such reactions are termed as cleavage reactions. The most important cleavage reaction of alkenes is ozonolysis, that is the cleavage of double bond with ozone. The complete reaction consists of addition of ozone to the double bond to form an ozonide, followed by decomposition of ozonide to yield the lower fragments, which consist of aldehydes or ketones. The decomposition is generally carried out in the presence of reducing reagents such as zinc, dust, and water. For example, propene plus O2 gives ozonide. Then H2O is added plus Zn and it gives ethanol plus methanol. If the ozonides are decomposed only with water, H2O2 produced during the reaction would oxidize the aldehyde initially formed to the corresponding acid. Since does not allow further oxidation to take place. Let us now consider the two stages of the reaction separately. Addition of ozone, ozonization. Ozone reacts vigorously with alkene to form a highly unstable compound called initial ozonide or molozo- molozonide, which undergoes spontaneous rearrangements to give relatively more stable product called ozonide as shown below. Second is ozonolysis. Ozone The ozonides are themselves unstable compounds. They are not isolated but are reduced directly with zinc and water to yield aldehydes or ketones. Applications of ozonolysis. The final product obtained by the ozonolysis of alkenes consists of one or more aldehydes and ketones, depending upon the nature of the groups attached to doubly bound carbon atoms. It may be noted that if the carbon forming the double bond carries the hydrogen attached to it, it would give rise to an aldehyde. If it carries only alkyl groups attached to it, it would form a ketone. For example, 2-methylbutene plus O3 gives the ozonide. Then in the presence of H2O and zinc, it gives propanone plus ethanol. Since no two different alkenes can give the same combination of aldehydes or ketone as the final product, it's generally employed for locating the positions of different double bond and identification of alkyl groups present in an alkene. Thus, ozonolysis plays an important role in the structure determination of organic compounds through their degradation into similar fragments. Illustrations of the application of ozonolysis. Let us try to locate the double bond, identify a 6 carbon alkenes which yields a mixture of acetone and pro- propionaldehyde in ozonolysis. Acetone contains two methyl groups attached to carbonyl carbon, while propionaldehyde has one ethyl group and one hydrogen attached to carbonyl carbon. We know that during ozonolysis it is doubly bound carbon which change into carbonyl group. Therefore, it can be concluded that one of the doubly bound carbon of the given alkene carries two methyl group while the other doubly bound carbon carries one ethyl group and one hydrogen. Therefore, the given alkene should have the structure this. The double bond is obviously located between 2C and 3C carbon, third and second carbon. The complete sequence of reaction may be depicted as 2-methyl 2-propentene ozonolysis and gives the ozonide, and after the addition of H2O and zinc it gives acetone plus propanaldehyde. Simplified procedure for identification. There is a simplified two steps procedure for the location of double bond and the identification of alkenes as shown below. Step 1. Write the structure of the products of ozonolysis with carbonyl groups facing each other. Second, remove oxygen atoms from carbonyl carbon and connect them by a double bond. That is 2-methyl 2-propene. Thank you.